Alright, so we are back to looking at the periodic table. So we're going to go over what each of these groups means. Some of the words that we go over you might not know right away, but we're going to go through definitions as well. So we're going to start with the alkali metals. So remember, that's the first group that we have here, our alkali metals. So alkali metals are less dense than other metals. So going through your notes, make sure you fill these in. We'll go through one by one on this. So they also only have one valence electron. So remember, valence electrons is the outermost shell of electrons that all of these have. So if we draw the Bohr diagram for lithium, they only have one in their outer shell. We can draw our Lewis dot diagram for lithium, which just looks like that. So it only has one electron in its outer shell. And you can tell because it's in group 1. So alkali metals also, their reactivity increases moving down the group. So as you go this way, their reactivity increases. They have the largest atomic radius of their period. So going this way, they are the biggest. So lithium would be bigger than beryllium, and beryllium would then be bigger than boron. Okay? Alkali metals have a low ionization energy and very low electronegativity. Alright, so if you don't know what some of those words are, that's alright. We're going to go over some definitions after and see how they relate to different things. So the next one that we're going to go over is our alkaline earth metals. So I'm going to do those in green right here. So our alkali earth metals, they have 2 valence electrons. Again, I'm going to point you to the group number. It's 2A. So they have 2 valence electrons. They have a low electron affinity and a low electronegativity. So that's all you really need to know about this group right now. So the transition metals is this big block of yellow that we have over here. I'm not going to color them all in because you guys have already done that. So transition metals, when you think of a normal metal, they're going to be hard and shiny, but there's 2 specific words that I want you to know. Transition metals are ductile. See if I can write it. Alright, so ductile, meaning that they can be stretched pretty far, making wires and stuff out of them. And the other thing that they can be is malleable. So they can be molded into a lot of different shapes. Alright, so those are the 2 words that I want you guys to have for what do they feel like. Hard, shiny, ductile, and malleable. Alright, so transition metals have a high melting and boiling points. So they don't melt very easily. They have a high conductivity. So conductivity is the ability to transport electrons in an electric current. So when you look at the bottom of a pan, you'll notice that it looks like copper on the bottom. That's because copper is really good at moving heat and electricity. Transition metals have a low ionization energy. Alright, so we're going to move on to metalloids. Do this in yellow over here. Oop, no, red. They're going to be red. So our metalloids have an intermediate electronegativity and ionization energy. So they're sort of in between metals and nonmetals. So what do metalloids look like? They have the same metallic luster that metals have, so that same shininess. And the reactivity depends on other elements in the reaction. So if we have boron over here, and boron decides to bond with lithium, it's going to be an entirely different reaction than if it goes to bond with something like magnesium. So the reactivity changes depending on what the metalloid is bonding with. So that's the same as people. you are outgoing around certain people and closed and not very happy around other people, that's the same as metalloids. They don't like some people. All right, and we're going to go head over to non-metals. I'm going to do those in purple, same as we did before. So our non-metals have a high ionization energy, a high electronegativity, and they're very poor conductors, so they don't move electrons very well. But they're very, very good at gaining electrons, so they can pull electrons away from other atoms. The next ones we have are the halogens. So our halogens are these right here. And our halogens have an extremely high electronegativity, and they're very, very reactive. So the reason that they're so reactive, we're going to go back to the valence electrons here. So they have 7 valence electrons because they're in group 7. So we're going to take a look at fluorine for a second. So fluorine, if you remember our Lewis dot diagrams, has... Oop, guess I can't draw there because I've got a text box. So fluorine has 7 different valence electrons. Right? And so valence electrons, they want to have 8 in their outer shell. 8 makes them happy. So fluorine is so close to getting that 8th electron, that they're going to pull it from anything. So something like lithium over here is going to lose that electron very easily to fluorine. So fluorine's going to rip that electron away. And lithium wants to get rid of that electron. It doesn't want that one electron because it wants to be happy with a full outer shell as well. So that is why halogens are extremely reactive. The same thing goes all the way down the column. They all have 7 in their outer shell, and they all really want to take an electron from somebody. So the next ones that we have are noble gases. So noble gases is kind of a wonky name for atoms. Why would they call them noble? So the reason behind that is because noble gases here, I'm going to draw the Lewis dot diagram for one of them. So I'll do neon. So neon has a full outer shell of electrons. So it has a full 8. It is content. It is happy. It doesn't want any more electrons. All right? So that's the same for every other one in this shell, in this column, because they all have 8. So they can't take any more. They don't want any more. So they're not really good at bonding. They're very non-reactive. So they have 8 valence electrons. They have low electronegativity because they don't want to take anyone else's electrons, and they're non-reactive. All right. So the next thing that we're going to move on to is the next page that has some definitions. So this is where we're going to get some clarity on what these different things mean. So the first one that we have is electronegativity. So electronegativity is the measure of how strongly an atom wants an electron. So something like fluorine will have a really high electronegativity because it really wants an extra electron. So again, electronegativity measures how strongly an atom wants an electron. An atom will take an electron. So the greater the electronegativity, the greater an atom's attraction for electrons. So fluorine has a high electronegativity. Lithium would have a low electronegativity because it wants to get rid of an electron, where fluorine wants to take one. So the next one we're going to look at is valence electrons. So, not valence electrons, sorry, ionization energy. Ionization energy is the energy required to remove an electron. So again, we're going to use fluorine and lithium as our examples. So fluorine has almost its full outer shell. It's almost happy. It's almost there. fluorine is not going to give up an electron very easily. Because if it gets rid of one, then it's just one less closer to getting one. So something like fluorine would have a very, very high ionization energy. So it's very hard to remove an electron. Something like lithium, that only has one, it would be very, very easy to get rid of lithium's one electron, because it wants to get rid of it. So lithium would have a low ionization energy. So valence electrons, we've already talked about these, but valence electrons are the electrons in the outermost shell of an atom. So when you draw a Bohr diagram, I'm going to do carbon for an example. So we got carbon in the middle. This is not a great drawing, but carbon has 2 on the inner shell, and then 4 on the outer shell. So these 4 here would be our valence electrons, because they're on the very outermost shell of this. Alright, so conductivity and conductors. So we talked about this already, but conductivity is the degree to which certain materials conduct electricity. So it's the flow of electrons. Can they conduct a flow of electrons? So remember, our metals are really good conductors. Alright, electron affinity. So this one has some complicated stuff to it, but the only thing I want you to remember is that electron affinity is an atom's likelihood of gaining an electron. So again, we're going to use lithium and fluorine as our examples. So fluorine, with its 8 different valence electrons, 7 different valence electrons, and lithium only with its 1. Lithium would not be very likely to gain an electron because it's trying to get rid of an electron. Fluorine is extremely likely to gain an electron. So fluorine would have a high electron affinity. Lithium would have a low electron affinity. Alright, and then there's one more that I want to go over that I didn't have a chance to type on the back, because I forgot about it until I handed it out. So what we're going to do now is go over atomic radius. Alright, so radius you normally think of with the circle and the line drawn out from the circle. And the radius is that line right there that you can calculate and measure in your math class, but we're not going to do that. Atoms are so small that you can't even begin to measure the radius of them. So we do the generalized idea of how big or small an atom is. So what we said before was the atomic radius is the general size of an atom. So we talked about the alkali metals and how as you go across a period, the alkali metals are the largest one. So something like lithium would have a bigger atomic radius than beryllium, than boron, than carbon, nitrogen, oxygen, until you get all the way down to fluorine, which is just a teeny tiny dot. Atomic radius also increases as you go down the row. So lithium would be the smallest here, and you got sodium, potassium, rubidium, cesium, and then you got francium, which is a huge, huge, huge atom. There's a little nucleus right in the middle. So that's the atomic radius, is the radius with the electrons on the outside. So we're going to go over this more in class. So this is just an introduction on why things happen.